Hey everyone, I thought I'd make this quick video going over the mathematics of machine learning. Here I'll kind of go over underflow and overflow, poor conditioning, and then gradient-based optimization. Starting off, underflow is when there's a rounding error where the numbers near zero are rounded to zero. So this can be like a very small number like 0.001 is just equal to zero inside the eyes of the machine learning model. And although this may seem like really trivial in this case, it actually leads to a lot of big problems when running machine learning models. Same thing with overflow. It said like if it's like 999,000, then that it has approximates to infinity. That can cause really big issues. So that this is fixed is through the softmax function. It actually does e to the xi over the sum of all of the e to the xi probabilities. And over here, this fixes the overflow and the underflow issue because e to the 0.001 is just 1, and this won't cause any issues for the machine learning model. If you see below, this is all the probabilities are all done from a scale of 0 to 1. So when whatever output layer, whatever values you have, it can all be normalized into a thing between 0 and 1. But of course, there's still some issues with this because if C is very negative or our value is very negative, then EXPC will then underflow, which means that e to the negative infinity is basically 0, and then e to the infinity is a really large value of infinity, so that would overflow. So another way we can do this is actually using a softmax of z, where x is equal to a max of xi times xi, so that it removes the overflow issue as well. Another thing that also we talk about is conditioning and how rapidly a function can change with small changes in respect to its inputs. So over here, you can see that the condition number, or how fast a matrix would change according to the small changes in its inputs, it can be done by the eigenvalue of I over the eigenvalue of j. And this is just a very simple way of seeing if your matrix is really susceptible to changing, especially if you're looking at overflow and underflow and seeing how fast the matrix actually change inside of a particular model. Next, we'll be going over is gradient-based optimization. I'll be expecting you guys to know a little bit about derivatives, local minimums, local maximums. So a main thing about gradient descent is basically if you start off with this cost function, where cost function can be like inside of a least squares linear regression, you're basically trying to get to that optimal minimum. So what we're going to do is try to figure out how we can actually set this learning rate and find this objective function that we want to minimize. In this case, it'll be the cost function. Through this thing called linear approximation, we can kind of figure this out. So we have our original f of x value, and then over there, using this epsilon, this learning rate, we can actually decrease it using the derivative of x. Over here, you can see that if we start with this value, and then we actually get the slope that's there at this point, then we can just move in incremental steps, and we can slowly go down to the minimum by following that function. Because basically a linear approximation is that you can basically set the tangent line, and then it'll slowly reduce, and it'll kind of mimic what that function is doing for really, really small steps. At the end, we want to get to that minimum cost, because remember, the whole goal of machine learning models actually minimize the cost function. We don't want to get a really large error at the ending. So over here, this is kind of a graphical representation in a 3D vector space. You can see that over here, here's a maximum. The red areas are maximums, and the blue areas are more minimums. So we want to reach that local minimum. And this can be done using derivatives. So we just keep going down that slope over and over. And this can kind of be, so this is for kind of like just a 1D or 2D vector. But for large dimensional vectors, we can actually make these gradients, where gradients are essentially just a vector of all of the first derivatives. And through this, running the partial derivative with respect to xi, then we can actually find the directional derivative. So directional derivatives are basically, it can move either like right, left, up, or down, and it's just moving in all different types of directions. And what the gradient does is it stores all these directional derivatives, so you can figure out basically where the vector is moving inside this particular space. And what we want to do is trying to optimize it so the gradient is really close to 0. So all of these values of all these directional derivatives are really, really close to 0. Because at that point, where we hit a local minimum is basically where inside the graph, it just reaches a minimum where the gradient is equal to 0 and there's no really underlying slope. And through this, we can use something called the method of steepest descent, where we just start off with the initial thing. We just need machine learning models to start off with the random x value, input value, and they slowly diverge to this learning rate. This learning rate can be optimized as much as you want, and the f of x slowly decreases using the tangent line approximation slowly until it finally reaches the local minimum at the ending. And this is done incrementally until we finally get that final value at the ending. And different ways you can set the learning rate. We can make it a really small value. Usually it's between like 10 to the negative 4th to like 10 to the negative 2nd. Or we can use a line search. We can kind of evaluate different epsilons, where we can choose several values of e and then find which one leads to the smallest objective line function value at the ending. So that's kind of a quick overview of gradient-based optimization, poor conditioning, and overflow and underflow. In this book, I also found a lot of different other things, like going over Jacobian and Hessian matrices, continued optimization, and linear least squares. I'll be going over that in a later lecture. Thank you for listening, and I'll probably post another one soon.